The correlator demodulator is shown in this block diagram, and you can observe that there are two branches, the upper branch and the lower branch. So the received signal R of t, when it passes through the upper branch, it is multiplied with S naught of t. Now we have taken S naught of t and S1 of t being the two orthogonal signals, right? So in the upper branch it is multiplied with S naught of t, and then this product is integrated. And the output of the integral, this integral is observed at the instant t equal to tb. So this sample is observed. The value of this sample is r naught, right? The value of this sample is r naught, and this value r naught measures the similarity of the received signal with S naught of t. Similarly, in the lower branch, if you observe, the signal R of t passes through when it passes through the lower branch, and here it is multiplied with S1 of t first, and this product, the value of this product is integrated, and the output of this integral is observed, because it continuously is an integrator, so it's continuously giving you some output. The output would be observed at this instant. So this sample value is important, and this sample value is R1. It is R1. This R1, the value of this R1, or this sample value, which is taken at t equal to tb, this is an important instant. This measures the similarity of R of t with S1 of t. So it measures the similarity of R of t with S1 of t, and that measure is given by R1. Now we have two values, R naught and R1. R naught represent the similarity of the received signal with S naught of t, and R1 represents the similarity of the received signal with S1 of t. And based on these values, these values are input to the detector, and this detector, we will discuss it later on, it's a maximum likelihood detector. So these values are input to the detector, and the detector decides whether the received signal is S0 or S1, right? So the detector actually decides whether the received signal is S0 or S1. So if we see that this output is it is given to the detector. So how the detector analyzes these two waveforms. So it observes, it has two values now, R0 and R1, and it compares these two values. If it finds R0 greater than R1, if the detector finds that R0 is greater than R1, then it decides in favor of S0, which means that the detector give us the knowledge about R of t, and it declares that your received signal is S0 of t plus n of t. This is what it declares, which means it the based on R0, based on R0 being greater than R1, it says that the received signal is S0. However, if it finds R1 greater than R0, then the detector declares the detector take decision in favor of S1 of t. It is in favor of S1 of t, which means that the detector declares that your received signal is S1 of t plus noise, right? Now once the signal is detected, because the receiver already knows that your 1 is represented, they already had an agreement, the transmitter and receiver, that 1 would be represented by S0 and a 0 would be represented by S1. So when it declares that S0 is the noisy signal actually is more like S0, the receiver outputs a binary 1. And when it declares that when it detects that R1 is greater than R0, then the detector would output a binary 0. This is the how the detector gives you output. So this output would be a binary 1 or a 0 based on the values of R0 and R1. Now let's do analysis. Let's see our signal. Specifically, we would observe our signal at these points. Let me give some name to these points. So I'll analyze the signal in the upper branch first. So we would like to process our signal in the upper branch, and I would see the this is point, suppose this is my point A, and then we have another point B, right? And the value of this B is observed at t equal to TB, which is R0. So we would write an expression for the signal at the input of the integrator, and then we would see the signal at the output of the integrator, and then we would see the expression, mathematical expression for R0. Let's see these expressions below. So we have this block diagram, this circuit, and if I try to write an expression at point A, so specifically at point A, I have the product of R of t, I have the product of signal R of t and S0 of t, right? This is the product. For analysis, let's assume that our transmitter has transmitted. Suppose we assume, now this is our assumption. This is our assumption. Suppose our received signal, which is Si of t plus n of t, is actually equal to S0 of t plus n of t. Suppose our received signal is actually equal to this one, which means that the transmitter has transmitted S0 of t. This is our assumption, right? This is our assumption that the transmitter has transmitted S0 of t. You can later on, when we process our signal with this assumption, you can also assume that the transmitter has transmitted S1 of t, and then see how the correlator demodulator would give you how the correlator demodulator would process it and would give you some output. So suppose in this first assumption, we say that the signal is this is our received signal. So if this is our received signal, we would expect that our correlator demodulator should find R0 greater than R1, right? It should find R0 greater than R1, and it should declare that our received signal is actually it should take decision in favor of S naught of t, and it should give us an output data 1. This is what we expect, but let's see what actually this is the we have written the expression for at point A, the received signal, the product, not integral actually. At point A, we do not have integral, right? So we just have this product. At point A, we just have this product. Now, let's see this product at point A. At point A, this product is R of t into S naught of t, and actually because we said that this is our first assumption, so substituting this assumption here, we have S naught of t plus n of t, right? This is our R of t, and it is multiplied with S naught of t. So we have our R of t multiplied by S naught of t. This is the signal at point A, or if I write it, if I just multiply this one, it is actually S square t plus S naught of t and n of t. So this is our signal at point A. Now this signal is input. Let me write it, my input signal to the integrator, which is I just say this is I of t. I give it a name I of t, which is input to the integrator. Now this is input to the integrator. The output of the integrator, we can write the output of integrator now, and the output of integrator would be the output of the integrator, which is the signal at point B actually. The signal at point B is the output of the integrator, which is the integral of this product, right? It is from 0 to t, instant t, the integral of this product. Well, to be accurate, we should instead of t variable, let me use the tau variable here. I should use the variable tau. It is just replacing t by tau in this equation, right? Just replacing t by tau in this equation. So if I replace t by tau, what I can write? If I replace t by tau, I can just write my I. Let me erase this one as well. So if I want to write tau, my I of tau would be S naught square of tau, and this, right? This would be my equation. It's the same equation, just replacing t by tau here. So now we are having this integral, right? We are having this integral, and this integral means we are actually integrating. We are actually integrating from 0 to t S naught square tau dt plus 0 to t S naught of tau n of tau dt, right? Because we are sorry, this should be d tau, and I did one mistake. You should correct it here. This should be d tau, because we are using the tau variable now. Limit is t, but we are using the tau variable, so I'm making this correction here. This should be tau, this should be tau, this should be tau. Now we have to observe this integral. This is the output of the integral. This is the output of the integral, which is 0 to t I of tau deta, right? This is the output of the integral at any instant t. At any instant t, this is the output of the integral. We are interested in this output when this instant is equal to tb. Now, what's here? You can see the importance of tb. We are interested in this, the output. We are interested in this output at instant t equal to tb, or this particular value. So when we say t is equal to tb, it means from 0 to, we are interested in this integral when t is equal to tb. So here I am substituting t equal to tb. It's the same, and now I can say this is my r naught, because r naught is the r naught is this value when t is equal to tb, right? It is this value t is equal to tb. So let me write it in different color so that you can find later on when you compare it. So we have the t equal to tb. R naught is the value when this integral is t equal at this integral t equal to tb. So at this instant, so we are interested in r naught. So I'll just replace these limits. I'll put it tb, right, in the above equation. So if I say tb, this is the integral would look like this. It is from 0 to tb, s naught of tau, n of tau deta, right? Now if you closely observe this integral, what is this? This is actually the square of the signal. It is the energy of the signal. This is actually the energy of S naught. So you can find out this energy. I would just write it as a notation that this is the energy of my symbol S naught, and this is the energy of the symbol S naught, and this one, this part, I would write it as N naught. So actually I have the energy of the signal. Actually I have the energy of the signal and the plus N naught, the noise term. This is the noise term. This part is the noise term, which I represent by N naught. So I represent by N naught. So this noise term is represented by N naught. So I have the energy term and I have the noise term. And my received signal R naught, which is a number, it represents the this number is actually equal to the energy of the signal plus N naught. And this N naught, we would analyze this N naught. This N naught is Gaussian. This N naught is actually noise, and it is we say it is this N naught is Gaussian with mean 0 and variance sigma square. It is Gaussian. We say this and we represent it this way. So we say it is let me rewrite it. We say it is Gaussian. This N is actually Gaussian. So I would like to rewrite my N. This N naught, we say it is normal or Gaussian with mean 0 and variance sigma square. So this is the notation to represent this Gaussian noise term N naught. N naught is normal, this n for normal or Gaussian. So it has a Gaussian curve, with mean 0, and it has certain variance sigma square. So whenever you observe this type of notation, keep in mind that the n, if you want to plot the PDF of n naught, it would be Gaussian shape, bell shaped. The mean is 0, and this spread depends upon the variance, right? Spread depends upon the variance. Now we have this R naught, the number which is equal to the energy of the signal and the noise term. This is from the upper branch, right? From the upper branch. Now we would like to analyze our signal of the lower branch, the correlation, because the lower branch gives us the correlation of a signal with S naught, right? This is what we said, that the correlation of a signal with the so if you observe in the lower branch, if you go back to the block diagram and you observe the signal in the lower branch, initially you have the product. So your signal, received signal, is multiplied with S1 of t. As we said that our received signal, according to our assumption, our received signal is S0 of t plus n of t, noise, and that is multiplied with S1 of t. So our signal, the product, is actually S0 of t multiplied by S1 of t plus S1 of t multiplied by the noise. So this product is input to the integrator. So this I of t, I would say this is my I of t. This is input to the integrator, and the output of the integrator, we can express the output of the integrator at any instant t. The output of the integrator at any instant t can be expressed by this expression 0 to t I of tau t tau. This is the output of the integrator at any instant. So at any instant t. So we have the right, if you observe the right hand side, 0 to t, we have S0 of tau, S1 of tau, deta plus 0 to t, S1 of tau, n of tau, and deta. So we have these two integrals. We have the at instant t. Now once again we have replaced the variable. Again another the same mistake. Here we should have d tau, right? Here we should have d tau. So let me correct it, d tau. Now if we solve this one, or if we observe our sample value R naught, if you observe our sample value R naught, which is actually the output of the integrator. Here we should have theta. The output of the integrator from 0 to R. Sorry, this is not R naught. This should be R1, right? This should be R1. So we have R1 at t equal to, or let me write it in because this integral 0 to t, but we want this. We are now observing R1, so R1 is the sample value when t is equal to tb, right? So it is the same integration at this particular instant, t equal to tb. So when you say t equal to tb, you can rewrite your right hand side, put TV, S naught of tau, S1 of tau, d tau plus 0 to TV, S1 of tau, n of tau, d tau. Now if you closely observe these two waveforms, S naught of tau and S1 of tau, we already said that these signals are orthogonal. S naught of tau and S1 of tau are orthogonal. When the signals are orthogonal, this is the dot product of two orthogonal signals, and the dot product of two orthogonal signals is 0. So from here you would get 0. Now this one is S1 with the noise, and this is the noise term which we said it is N1. So we have the dot product which is 0 of two orthogonal signals, S naught of tau and S1 of tau. These are two orthogonal signals, as I mentioned in my previous video, that you are, if you recall, that your S naught of tau, S naught of tau, S naught of tau is from 0 to TV plus A. It looks like this. And your S1 of tau, orthogonal signal, right, from 0 to TV, this is S1 of tau. So plus A and minus A. So these two waveforms are orthogonal, and from here you get a 0. Their dot product is 0. So actually the received signal R1, the received signal or the R1 value, is just N1. Now if you compare it with our previous value of R0, which is the energy of the signal, S0 plus N0, the noise term. So R0 has two terms, the energy of the signal plus noise, while R1 is just the noise term. And we expect that this summation, which is the summation of two numbers, two values, this summation is greater than just this noise term R1. We expect most likely this sum is greater than just this single term noise, or R0 is greater than R1. So whenever the detector finds R0 greater than R1, it would declare that your received noisy signal, or R of t, your received noisy signal R of t is actually S0 of t plus N of t, which means that the detector detects the transmitter has transmitted S0, and it would output a 1. Which is the representation of S0. It would output a 1. Now in the absence of noise, we can draw the output of correlator. So let's try to draw the output of correlator in the absence of noise with the same assumption, right? So we are having the same assumption. If now let me draw the output of the correlator. Now if you observe graphically, we said that our signal, this is 0 to TV plus A, and this is S0 of This is S naught of t, S naught of t, right? So if we observe the same now at zero instant, what we would now this is we expect that our signal r of t, this is our signal r of t, and we would like to draw the output of the upper branch and the output of the lower branch, right? The output of the lower branch. So this is the output of the upper branch, right? And below this I would like to draw the output of the lower branch. So this is my or you can say this is my R0 and this is my R1, the output of the upper branch and the output of the lower branch at time axis. Now at t0 we have this knowledge at the receiving end, S0 of t, but we have not yet received any signal. Now once we receive a signal, we would represent the reception, because this is what the transmitter has transmitted, this pulse. As long as this is not received, we are at this point. Now when some part of it is received, or let me show it by saying that it's dragged to this. So for some positive value of time t, we at t0 there is no overlap, or the signal not yet received. So there is because we are observing r of t product. Initially we should we have always we have to look at this product. So when this signal is 0, means nothing received yet, the product is 0. So we are here. As soon as we start receiving the signal, we get some product, and with the increase in time, this product increases. So we have certain value. So let me plot these values at TB, at instant TB, and at up to 2 TB. Now when we start receiving this signal, it means we are dragging it this way. So we will start receiving the product and the integral of this product R0, because we are now plotting R0. So as soon as we start receiving the signal, we get some product and this increases. You can always evaluate it. I'm just showing it graphically. When T is equal to TB, it means your signal completely overlaps. You get this signal, it's dragged to here, because you will, when you start receiving the signal, you would completely receive it when T is equal to TB. So you would get this signal when T is equal to TB. After the start up to TB, you would get a complete signal, and when you get a complete signal, you would have a maximum overlap of these two, and you would get your maximum value. So your product R0, actually at every instant it has certain value. So you can see at every instant you have certain value of R0, and this value is maximum at TB, when you completely receive your signal. This value is maximum at TB. Now after TB, the signal already received, no more signal. So it means you are just dragging it this way. and again this product decreases, and up to 2b it would reach to the minimum 0. It would reach to 0. So your output, the correlator output, is maximum at t equal to tb. You can see a correlator output is maximum at this point. That is why we try to observe this sample. We are just observing this sample, which is the product of the, which is actually s naught square, and s naught square, the integral of the square of the signal, and the integral of the square of the signal is actually equal to the energy of the signal. So we have energy of the signal at this point. We have energy of the signal s naught is energy. Now if you observe it in the lower branch, now if you observe R1 in the lower branch, in the lower branch we are multiplying S naught. Let me redraw it. For the lower branch I will draw these signals once again. We are multiplying this S naught. This is my S naught of t, and we are multiplying it with orthogonal signal, right? Sorry, in the S naught, let me draw it in the way it is. Actually we have R naught of t. We have R naught of t. R naught of t is the received noisy signal, right? R naught of t is the received noisy signal. Now I am observing it in the absence of noise, right? I would like to observe it in the absence of noise. So suppose this is my R of t. This is my R of t in the absence of noise. So it would be exactly S naught of t, and we are multiplying this with the another waveform, the existing replica. As our previous convention, we are plotting our existing replica here, right here. So let me do the same. Let me show it in another slide. It would be better if we put it on the fresh slide. So now we have our signal. We have S naught of t available at the. We have S naught of t. S1 of t. We have S1 of t available at the. This replica is available at the receiver, and we receive a signal. We receive a signal here, from here. This is our R of t at time instant t, and we would like to plot this product. We would like to plot R1 here, the output of the second correlator, or the output of the second branch. Now in the upper branch, in the lower branch, we are multiplying our received signal with S1. So as long as nothing is received, or you should say t equal to 0, we have no product, so we are here. At t equal to 0 we are here. Now I would draw it at up to tb and 2 times tb. Now as soon as we start receiving the signal, which is represented by this drag, right? I'm dragging it here. So we would get the product, and the product here, it is A, right? And this is also A. So we would get some positive value, and that positive value would depend upon the product, the integral of this product. So you can always evaluate it. So from here we would get some positive value. It would increase up to TB by 2. This is TB by 2. So the instant at here, this is TB by 2, right? This instant is TB by 2. So when your signal further received signal is, if you represent your received signal by this blue curve, received signal here. So we have all the positive area, all the positive product. You would get some greater value here. You can always find this greater value. You can always evaluate it. The exact number, we can always find the exact number. So you would get some value at TB over 2. Now, if it further, if we drag this waveform further to here, right? Or let me redraw it. Suppose we further drag it up to this point, so it would be something like this. Now if you see this, if you observe from in this instant, you have a positive value multiplied with a positive value, you will get positive. The net result will be positive. But from in this range, just this one, right? Only this one. The signal here is negative, and you have a positive, so the result would be negative. So you have a positive area, and then you have a negative area which is equal to this thing. The negative area will be equal to this. So this result would decrease. This result would decrease at TB, at this instant. We are actually having this 3/4 of the TB. So at this instant it would decrease. So you have an increasing curve at TB over 2, then it decreases, and when you observe this product at TB, that is when your signal completely overlaps. If your signal completely overlaps like this, your signal is shown like this. When it is completely received at TB, then you have a positive, the product with the positive area is the same as equal to the negative area, because this positive product with positive with negative would give you a negative number. So you would get 0 if you evaluated the integral. So actually the output of your integrator looks like this. The output of your integrator at TB, at instant TB, it is 0, which would further go this way. If you plot it up to 2 TB, you would see this curve. So at instant TB, in the absence of noise, you can see R0 is actually 0. This value is 0. So your R1 is actually 0 at instant TB, in the absence of noise. This we are observing in the absence of noise. While in the upper branch, we have seen that from the upper branch we have observed that R0 is actually equal to the energy of the signal, and R1 at instant TB is actually equal to 0 in the absence of noise. This is in the absence of noise. So R0 is, of course, in the absence of noise, your R0 is greater than R1, and the detector can easily declare that your transmitted signal is S0 of T, and the detector would output a binary 1. Now if you repeat this process for by having an assumption, if you repeat this process by having an assumption that your received signal R of T, which is equal to Si of T plus N of T, is actually equal to S1 of T plus noise, then you would see if you repeat this the same process by assuming that the transmitter has transmitted S1, you would see that R1 would be equal to the energy of the signal S1, and your R0 would be equal to 0 in the absence of noise. Of course, if there is in the absence of noise, you would observe these outputs, and in the absence of noise, it is from these outputs it is clear that R1 is greater than R0, and the detector would decide in favor of S1 of t, and it would output a binary 0. So this way the detector detects the signal. If you have noise, then your R1 would be energy of the signal plus noise, right? And your R0 would be 0 plus noise. This would be the case when you assume that your transmitted signal is or your received signal is S1 of t plus n of t. You can just repeat the same analysis and you would end up with these results, right, in the presence of noise. In the absence of noise, of course, you can get these values, and you can say that it is easily it can be detected easily. So I suggest that you do this. You just solve this circuit with this assumption and try to plot the output of the correlator by assuming that a transmitter has transmitted S1 of t and you have received a noisy signal which is S1 of t plus n of t.